Welcome back, everyone. In section 5.2, we are going to extend what we learned about Riemann sums, which were LRAM, RRAM, and MRAM, used to estimate the area between a function and the x-axis. And we're going to use some calculus, limit notation, to find not just estimates, but exact values for those areas. So to start out with, what we're going to do is we're going to sketch a couple of curves, and one's going to be a generic curve and one's going to be a quadratic function. And we're going to work through those in parallel or at the same time. So here's our generic curve. We'll call it f of x. And what we are interested in doing is finding the area between the curve f of x and the x-axis on the interval from a to b. And to do that, as you know, we would draw a bunch of rectangles. So I'm going to draw some rectangles here, and these rectangles have heights that correspond to function values. And what we're going to do is we're going to label x values within those subintervals, and we're going to call them C1, C2, dot, 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 CK, all the way up to and including CN. And that will be used to find the height of the rectangle, and those by plugging those C values into the function. And those C values can be anywhere within each of those rectangles. So the specific function that we're going to work with is the function f of x is equal to 2x minus x squared. And if you were to factor that out, you would see that it has zeros at 0 and at 2. 0 and 2, and it's a quadratic that opens down. So we're going to sketch that out, look like that. And we're going to do the same thing there with rectangles. We're going to draw some rectangles that have heights that correspond to the value of the function, and we're going to use values, x values within each of those subintervals to determine the height of those rectangles. And I will label those C1, C2, dot, 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 CK, all the way up to CN. All right, so what we're going to do is we're going to move from very specific parts of this where there are estimations of areas under the curve to the exact value. So what we're going to do here is we're going to break down each of these expressions and explain what they mean. So f of ck would be evaluating the function at each of the c values, and that would be the height of a rectangle. And delta x, just to be clear, delta x is what we are calling the width of each rectangle. So delta x would be the width of the rectangle, which would end up being the area of one rectangle. Similarly, for the specific function 2x minus x squared, you will see that we are evaluating the function at a c value, and that would represent the height. And delta x, again, is the width of each rectangle, so height times width, and that would equal the area of one rectangle. Well, to get an estimate for the area between the function and the x-axis, what we would have to do is we would have to sum up all those areas of all those rectangles. So this is where the sigma notation comes in. and the index k is the subscript for c, so k starts out at 1, so c1, c2, c3, c4, all the way up to cn, the last x value in the very right-hand rectangle. So what do we have? We have this part, the sigma notation, represents the sum, and this part, this is the area of a rectangle, depending on which c value you put in. So this is equal to estimated total area. Similarly, we are going to do the same thing. So we have the sum over here for the specific function, and this is the sum of the areas, I should have said areas of rectangles, plural, areas of rectangles. And this expression is the estimated total area. And here's where we transition, here's where we go into the calculus concepts, and we transition to the exact area. So you'll notice the only difference between this expression and the one above it is that we have this limit notation here. And what we're saying in this case is that delta x, the width of the rectangle, is going to 0. So as you can imagine, as the width of the rectangle goes to 0, the number of c values is going to go to infinity. So basically what we're doing is we're squeezing down the width of the rectangles to 0, which means we're going to approach an infinite number of rectangles, and when we do that, the function value at each of those c values is going to approach the exact height of the function there. So this is where the calculus part comes in. So basically what we have is this is saying number of rectangles approaches infinity. And then this is to the total area. So this whole expression is the exact, or approaches the exact area. And when we do this, what we do is we write this using this notation, which is called an integral. The integral from a to b, lower limit to upper limit, and that represents the sum of all the areas of the function to establish the height, and we use dx to indicate that delta x is approaching 0. So here we have the sum, here we have the height, and here we have the width. And if you remember from sigma notation, you evaluate what comes after it first. So you take the height times the width, you do that for all the rectangles, and then you add all those up. And to the right, we are doing exactly the same thing. So you can see number 5 to the right, or to the left, and basically what we are saying is we are taking the integral. In this case, we went from 0 to 2 of the function. Here we know the specific function, 2x minus x squared dx. So to get comfortable with this idea, we are going to work through some examples. And in this next example, what we're going to do is we're going to take what is representing the exact area and go backward and estimate it with a Riemann sum. And remember, a Riemann sum is simply estimating an area between a function and the x-axis by using some sort of geometric shape. We are going to use RRAM, which is rectangles. and we're using the right-hand side to establish the height. So here we have the function x cubed. I'm going to draw it from 0 to 3, and we are going to start out at 1. And it says use RAM4. So what we need to do is we need to establish the width of each of the rectangles. And the way we're going to do that is we're going to take the upper limit, which is referred to as B, and the lower limit, which is referred to as A. We're going to take their difference, so B minus A, over N, or in our case, 6 minus 1 over 4, or 5/4, to establish the width of each rectangle. And we are going to start at 1, so 1 would correspond to 4/4. And then we're going to add another 5/4 to that, so that would be 9/4, and add another 5/4 to that, which would be 14/4, and add another 5/4 to that, which would be 19/4, and one more time, which would give us 24/4, which is equivalent to 3. And since we are using RAM, we are using the right-hand side of the rectangle to establish each of the heights. And so I'm going to draw those rectangles in there accordingly, and we should have 4 of them because we're using RAM4. So let's show RAM4 using function notation. So RAM4 is going to be equal to, well, we have 5/4 times f of right-hand side 9/4 plus 5/4 times f of 14/4 plus ... 5/4 times f of 24/4, or 3. And we are going to write this now with sigma notation. So what we have is we have the summation from k equal 1 to, well, what are we going to do? We're going to do 4, because we have 4 rectangles, of the width of the rectangles. And here's the tricky part. We have to write the function so that it is correctly evaluated at the right-hand sides of each of the rectangles. So we know we have the cubing function. And I think the easiest way to do this is to start out with what we call our A value, the beginning value, and write an expression that increases that by 5/4 every time k goes up by 1. So we have our A value, 1, plus 5/4 times k. Now, to be clear with this is, again, this is considered a Riemann sum, an estimate of the area between the function and the x-axis. And if we wanted the exact value, what we would have to do is we would have to say the limit as delta x, or the number of rectangles, approaches infinity. So our upper limit of 4 would be n, and then out in front of it we would put a limit as n approaches infinity. And that would be similar to what you're seeing right here. Okay, so when you have that limit there, you have the exact value. And as we talked about on the previous page, we take that limit notation, which I am highlighting in yellow here, and we transfer it to what is called an integral notation. And they mean the same thing, but you will typically see it written as it is in the blue highlighted area. And so a few things about that. A is the lower limit of integration. B is the upper limit of integration. That establishes the bounds on the x-axis between what you're finding, the area between the function and the x-axis. The weird S-shaped thing is called the integral sign. It indicates summing that. As you know, f of x establishes the height of the function, and dx the width of the corresponding rectangles. And that implies that we are approaching an infinite number of rectangles, which means we are approaching the exact value. very briefly about this notation, which I'm going to highlight in green. The variable that you use does not matter, so you will see that changing. It's called a dummy variable. It still means the same thing. Take the function and find the area between the function and the x-axis. So as you can recall from first semester, with the definition, the limit definition of the derivative, we have this limit definition of the area or the integral, and the College Board is going to assess you on that. So we're going to do a little practice here with this, and we are going to convert from integrals to limit notation and back. So we'll start out with something that's relatively easy. The cosine function, we're going to integrate that from 0 to 5, and we want to write that using the limit notation. All right, so A is the lower limit of integration, B is the upper limit of integration, and we are going to find delta x, the width of the rectangles, by taking b minus a over n. So in this case, we have 5 minus 0 over n, or 5 over n. Our limit notation, so the limit as n, the number of rectangles, approaches infinity. We could say delta x approaches 0, but we're going to use this approach. The limit as n approaches infinity. The summation, our index, k equal 1, so the first value, to n, so we're going to have approach an infinite number of values. We're going to evaluate the function cosine at each of those values within each of those rectangles, even though they're approaching infinity. And the way we do this is we start out by evaluating at the a plus delta x times k. So in this case, we are going to start out evaluating at 0 plus our delta x is 5 over n times k. And then we are going to multiply it by delta x, and our delta x is 5 over n. So we have the necessary parts. We have the limit, which tells us that the number of rectangles is approaching infinity. We have the summation, which means to add up all the areas of all the rectangles. We are evaluating the function at a value within each of the rectangles, and that establishes the height of the rectangle, and then we are multiplying that times the width of the rectangle. And as you can see, as n approaches infinity, 5 over n is going to approach 0. So the width of the rectangle approaches 0. All right, number 2. So our delta x, b minus a, so 5 minus 1 is 4 over n. And we are going to write this again as the limit as n approaches infinity. The summation, our index, k equal 1 to n, our function, the cosine. Now this one's a little bit different because we are starting at an a value of 1, but our delta x is a little bit different as well. So 4 over n times k, and the width of our rectangles is 4 over n. All right. I'm going to do this next one with you, and then I'm going to pause the video and let you do 4 and 5 on your own. So, b minus a, or delta x, 7 over n, b minus a over n. So our limit notation, as the number of rectangles approaches infinity, summation, k equal 1 to n. The function is going to be x cubed, so we're going to have some expression in there. We're going to cube it, and then we're going to multiply by 7 over n. And again, our initial value plus delta x, 7 over n times k. Now you can drop the 0, and that would typically get dropped. I'm just putting it in there repeatedly so that you can see the pattern. So what I'd like you to do right now is pause the video, do 4 and 5, and then unpause the video, come back and check your answers. All right, so if you have to, pause the video again, take a look at the answers to 4 and 5. If you did not get those answers, please go back and try and figure out what you did wrong. The last thing we're going to do in this video is taking the limit notation and writing it as an integral. All right, so what do we see in this case? Well, first of all, things are rearranged a little bit. This 5 over n. So as I was saying, this 5 over n is our delta x. It's just in a different location. So we're going to move that. Well, think about moving it over to there, and this might be easier to see what we're doing. Our initial value, our lower limit of integration, is 2. And so this integral would be the integral from 2 to, well, I haven't figured out what the upper limit of integration is, but I know that b minus a is equal to 5, and I know that a is equal to 2, so b has to be equal to 7. So the integral from 2 to 7, so that establishes why our delta x is 5 over n. The function that we are evaluating is the natural log of, we'll call it whatever random variable we want, ln of u, because it's a dummy variable, times du. And the last one is even rearranged in an even stranger way. This pi over 3n could actually be put back in there, and pi over 3n could be written as pi over 3 over n. So our b minus a over n is equal to pi over 3 over n, or b minus a is equal to pi over 3. You will also notice that our a value is not there, which implies it's 0. So that makes things maybe a little bit easier. So we're integrating from 0 to, well, if a is 0, b has to be pi over 3. And the function that we're integrating is the tangent function. And again, we can put a dummy variable in there. So we'll put t dt. And that is it for today.